right, so let's wrap up section 4.2 here by doing a couple more examples of solving systems with the substitution method. So the ones we did last time I think were pretty nice to work with. Let's maybe just add a little bit into the process in terms of not much, not going to make it terrible on us, but so what we want to think about is, one of the reasons that we learned this technique is sometimes it's not nice in terms of graphing. And even just looking at the last example, we see that. Like if we were to graph those two lines, they would have crossed at 1530. Not too practical in terms of graphing. So let's look at another example here. So 2x minus 3y is equal to 2, and 6x minus y equals 2. All right, so we've talked about the process quite a bit, and hopefully at this point you will recognize that this y is the best and only best first choice to first isolate for. So maybe you can't always avoid it, but I think many times you will be able to avoid having to right away introduce a lot of fractions. So you try to pick a variable that has a coefficient of either 1 or -1. And in this situation, there's only one of them, and that's that second y. So we start by subtracting our 6x. And so that is going to give me my -y equals -6x plus 2. And then my last step on this isolating for y business is dividing both sides by the -1. Dividing each term in the numerator by that -1, we get our 6x minus 2. Also realize I kind of show that in a, I don't know, very traditional type of way. Honestly, another really nice way to think about that mentally would be to add y to the right and subtract 2 to the left. That might be another nice way to kind of go about that. All right, so once we have a variable isolated in one of the equations, we go into the other equation. So in this case, that means going into the first equation. And we want to take out the variable that we just isolated for. And so that's going to mean taking out the y. So everything else is going to stay the same. But we are going to take out the y, and in its place, we are going to put what we just isolated it to be in the first step, which is the 6x minus 2. Okay, if you can get there, you'll be fine, because then it's kind of, I don't want to say obvious, but it sort of just calls out to you to solve for x. So we would distribute through, be careful here, make sure you're distributing through the entire -3. So we would have the minus 18x, and the multiplying the two negatives, the plus 6. Combining your like terms, you'd have 2 minus 18 would be a -16. X plus 6 is still equal to the 2 on the right-hand side. With that variable term on the left, we'll go ahead and subtract to get our constants on the right. And so now we have -16x is equal to the 2 minus 6, which is -4. And now... And now my dog is making his appearance. Sorry. Love it. Okay, so we're at -16x. Buckley, stop. You see, he listened for about 10 seconds. All right, so we have -16x is equal to -4. And so the last step, of course, is to divide by that coefficient of -16. All right, so be careful. Don't just assume when you see 16 and 4 in division that your answer is 4. So this is 4 over 16. So it reduces to 1/4, not 4. So this is another good example of where solving with graphing wouldn't work out so well for us, because we're getting an intersection. These two lines are crossing at like a fractional location, and we couldn't just read that very readily right off of a graph. All right, so we have x equals 1/4. Again, we want to go back to, and I say, go back to that first equation. So go back to that little guy right there. And so y is going to equal 6 times, and then replace the x with the 1/4. And so we're solved for y, so now we just have to do the arithmetic on the right-hand side. So you're not going to always be able to avoid fractions. In that first step, when we pick a variable that doesn't have a coefficient other than 1 or -1, that helps. But of course, sometimes you're going to get fractions, like these have fractional answers. So 6 times the 1/4 is multiply numerators, multiply denominators, 6/4, which would reduce to, they're both divisible by 2 there, and 2 goes in to 6 3 times and into 4 twice, so it reduces to 3/2. So if I'm now subtracting fractions, think of the second one as being the 2 over 1, getting a common denominator. So now we would have fraction operation here of 3/2 minus 4/2, and then doing the 3 minus 4, we have our -1/2. So that is our y coordinate. So our final answer, x is 1/4 and the y is -1/2. Okay. All right, so let's take a look at one last example in this section before we go on to another algebraic technique in 4-3. All right, so number 4, we're going to have x minus 3y is equal to 1, and 2x plus y is equal to 9. All right, well, I think we're back to 2 different good choices to first isolate for. Last time we isolated for a y, so just to change it up, let's isolate for the x this time in the first equation. Either the first x or the second y would both be good choices here. So let's start by adding the 3y to the right-hand side there. So that's going to mean our x is going to equal 3y plus 1. Next step is to go into the other equation. So in this case, that is the second equation. And we're going to take out the x, and in its place, we are going to put what we isolated x to equal in the first step. And that was the 3y plus 1. So that goes in for x. Hopefully this is becoming a little more familiar and a little easier now than a few. And everything else stayed the same in that second equation. So now let's distribute. We would have 6y plus 2 plus y is equal to 9. And just combining our like terms here, so 7y plus 2 equals the 9. And then y terms on the left, let's go ahead and get our constants on the right. So we will subtract that 2, and now we have 7y equals 7. And then last step here, dividing both sides by 7, we get our first variable, y equals 1. And again, either equation, I like the one that we've already isolated for. I should say any equation, any of them that have an x and a y in them, to get the second variable. So x equals the 3 times the y, which we now know to be 1 plus 1. And so that's going to mean x is going to be 3 plus 1, which is 4. So our final answer on this one is 4, 1. Okay, and again, on any of these, if you wanted to always, sub them back into the original equations and check, that's how you'll really know for sure that you got the right solution. So if I subbed the 4, 1 back into the first equation, that would look like 4 minus 3, and that certainly is equal to 1. If I subbed the 4, 1 into the second equation, that would look like 8 plus 1, and that's certainly equal to 9. So that's always an option too. All right, so that wraps up section 4.2. When we come back next time, we will take a look at another algebraic technique to solve systems, and that's what we'll start with next time.